Okay, welcome everybody to RTOP for September. Currently, we are planning on, the current plan is to do the Western Conference in Owens Valley. And if anybody hasn't been there, it's a ski resort town in California. And it has all the dishes within, you just walk to the dishes. They're so close, and we got tours inside the dishes and everything. And we're working on that. The timing is somewhere in March timeframe. They're still trying to nail that down. And anyway, think about that. There is a small airport there. And so we're trying to get that, but the airport starts closing down. We wait too long. Like I don't believe the regional airport's open in April. So that's the kind of timing we're into. And we've got a lot of good talk on phased arrays that people have been working on the ezRA, getting their ezRA systems up, and various other things. Let's go to Andrew. You got something?
Nope, you're still.
You're on mute. Andrew, you're on mute.
Yeah. So, sorry, if you could ask somebody else to speak first and then come back to me in a moment. I'm just trying to pull something up.
All right, Dimitri. I had Dimitri on. Just a second.
Rich, are you calling for me? Okay.
Here we go.
Hello to all. Thanks, Rich, for possibility of speaking. I am working on project 43 gigahertz project. Maybe next month or two, I will be not too active in online meetings. Here I have just a moment. You can see my small dish, very small dish. Yep. 43 gigahertz telescope. Here it's tracking the sun. Now it's working from supply from AC supply 50 hertz, but I'm preparing it for working in field conditions from batteries. You can see I am preparing autonomous for supply for the dish, and I need for now to develop it up to the first flight tracking. I do not consider sun tracking is a first flight. Also, for today, I have a short report about 6.7 gigahertz major observations. This is measured in G09.61 plus 0.69196 point measure in this object. G09 is name for short. 1 year ago, I have some observations of this measure. Just for remind, data from Japanese data for this measure. This is star forming region as supposed for this coordinates object in these coordinates. some variability and periodicity were reported. About 250 days of period from this plot. Two strong lines. Peak up to 6,000 Yansky. In Moscow, this measure is rather low, up to 14 degrees of elevations. Very strong measures in Edward list of brightest measures. It's top first. It is top first. Also pictures of infrared spots from this object for long infrared, very clear spots of very clear spot is detected for GO9. Observations were made. Observations. Just a moment. I should switch off my camera. Okay. 2.4 meter dish used for observations. About 100 Yansky minimal detectable peak flux density, but measure is very strong. This is not too important. 1 year ago observations of this measure. You can see strong peak up to 4,000 Yansky. Unfortunately, my levels is somewhat lower than Japanese. This is some systematic difference. I don't know why this difference is. And strong peak up to 4,000 Yansky in 500 Yansky lower peak. Very strong and seen already 10-20 seconds of integrations very well. And recent observations, August and September, were made. Some variability is seen. Highest peak is somewhat lower, and distance between two peaks is a bit higher than 1 year ago. You can see about 1.4 kilometer per second difference here, about 1.6 kilometer per second difference in velocities of two peaks. And second observations several days ago, also about 3,000 Yansky highest peak, about 500 Yansky lower peak, and some info about this measure, periodicity from literature to 243 days, and next highest level for this measure can be expected in 1.5 months, and velocity drift of fishes also notice it. The distance, the distance of between two strongest peaks rises, but work 2 describes lesser drift rates then in my observations, maybe some maybe some errors in velocities in my observations. This all for today. If some questions, I will be glad to answer.
Okay, any questions for Dimitri? All right. Dimitri, on your sun tracking setup, have you tried to do there's an approach where you can actually figure out what the what's it called? But you can actually get the sunspot numbers by taking a certain measurement, I think at 10.7 centimeters, and then that converts to that's in direct relationship to number of sunspots. So,
If you're talking about 43 gigahertz tracking, no sunspots and solar activity can impact on levels of levels of sun flux. 43 gigahertz is rather high. Just a little dependence on activity at these frequencies. For 6.7 gigahertz is rather is more noticeable dependence on activity, and for 7.7 gigahertz is needed, and lower frequencies is more sensitive to solar activity, certainly. You can see as measure of solar activity the data from NASA Space Weather Center is very good data. Rich, I have answered to your questions. I will. It's okay.
I missed that question. I'm sorry. Okay. All right. Thanks, Dimitri. Andrew, are you ready?
Okay, thank you.
Yeah. Yes, I am. Yep.
Okay, we're going to go to Andrew.
Yeah, hi. So hi guys. So I was just saying at the beginning, I'm still buzzing because I've just returned only about an hour ago from the European Conference of Amateur Radio Astronomy, which was this year held at Harwell campus in the UK, which is the first time it's ever been held at the UK under the auspices of the British Astronomical Association Radio Astronomy Group, and we've had a fantastic time. I was talking about hydrogen line observing, and as you would expect, I was demonstrating some telescopes. I had one of Alex Pettit's Yagis, which was actually actively demonstrating collection of hydrogen. You could see the hydrogen peak very easily on it. And I also had remote access through to the two telescopes I had working here at home as well. And it was an opportunity to tell a lot of people about TED's Easy Radio Astronomy and show it in action there. And also to talk about SARA and the support and work that you guys do. And obviously talk about Alex's Yagi, and there was interest in all of those. And I also had a poster with the results, the mapping exercise that Jason and I had done of nearby galaxies using the 20-meter Skynet dish. So a chance to talk about that, and again the benefits of SARA membership. So I'm hoping that as a result of this, there will be more interest in radio astronomy, in joining SARA, in the Scope in the Box project, in ezRA, and hopefully Alex will get some orders for his dish as well. You might not know that at this moment in time, you cannot buy a New Alex Sawbird H1 anywhere in the world, as far as I know. They seem to be completely out of stock, and I suspect that's a result of all the discussion that we've been having on hydrogen observing, plus the BAA Radio Astronomy group, Hydrogen Line group meetings online. I think might have just denuded the world of its stockpile of Sawberts. So I'm sure that New Elect, being the sort of company they are, will get a whole pile in more from China before long. But nevertheless, it just shows that there is some interest and excitement in that type of astronomy. And I think it's because people can see something very practical, i.e. a map of the Milky Way coming out of it at the end. And so I'd just like to thank SARA for all the work that it's done on these sort of things over the years. It's wonderful manuals and support that it gives to people for doing these things and helping people to get started in radio astronomy and keep up the great work is what I would say. Anyway, I wanted to show a little bit of something tonight, which I will just pull up and remember how to do share screen. Get my emails out of the way. Right. So what I've had a go at doing, and I know Ted's already, I said these things back to him before, and so I'm going to admit the issue, maybe ask what everybody else thinks about this, and I don't mind whatever answer comes back. But I thought I have the 3 different telescopes all collecting hydrogen data, and I wondered whether it was possible to combine the data together to generate a better a better plot or a better set of plots at the end. Now they are slightly different. One's a 1.5 meter dish, one's an 86 centimeter by 86 centimeter 4x4 dipole array, and one is an Alex Pettit Yagi. I found that if I took the original data files that were collected in ezCol, which is the collection software in Easy Radio Astronomy, I couldn't process all those together. But then, if I processed the different telescopes, the first part to create the sort of intermediate files that are used in ezRA's processing steps, I found I could actually run the later Python scripts that process stuff in ezRA to actually combine all the software together. What I'm not sure is the validity of it. When Ted and I were testing it, we were wondering whether perhaps it wasn't valid. But anyway, just on the assumption that it is valid for the time being, for the sake of this discussion, this is the sky coverage that I get with this data. This will be about 2 million samples. I don't know why there's the gap at the top, I think, is due to the fact of what happens at very high angles. As far as my mount is concerned, it starts to jump large gaps, I think. I'm not 100% sure, but I think that's the most likely scenario. I have to look at it again and see if I can drill some holes that are closer together to try and get that gap filled in. But see, but you can see the limits in terms of top and bottom in terms of the part of the sky that I can cover. When you look at how the maxima fit in with the Milky Way, it does quite well. Reasonably hits the Milky Way on both sides. And then that shows a velocity plot against galactic longitude. I would say it's a little bit cleaned up to make it look. So this data has been a little bit cleaned for presentation purposes. I would just point out with some of the outliers removed, so it looks a bit better than it really is. But nevertheless, it gives an indication of the velocity areas with the longitude that's coming out in my data. And again, here we are. Here's the results of trying to weigh the Milky Way out to 8 kiloparsecs, which is where the king is. Where the sun is located. We obviously can't go any further than that. So we get a pretty good mass map going out to 8 kiloparsecs. And now we get on to the actual map of the galaxy itself that comes out, and you can see we're starting to pick up both the Perseus arm and an indication of the Norma/outer arm there as well outside of it. That's just looking at it slightly differently, and then that's overlaying it on a map of a professional map of the galaxy to give you an idea what it is that we're able to pick up with this data. So it does at least superficially appear to work in terms of giving us a mapping exercise. But again, the question perhaps is how valid the combination is. And there we are trying to demonstrate dark matter, which again seems to work reasonably well with this exercise. Again, showing that there's not a Keplerian rotation, that we're having a pretty much a flat line coming out. Okay, and then something else I'm to show a little bit. I used RNN 3D and just generated a 3D map there, which you can see that the normal outer arm shows up far better, interestingly, in the 3D map. I still am amazed that it is possible to create three-dimensional maps of the Milky Way using backyard data. I think that's absolutely incredible. And I was showing some of this stuff at UCARA, and again, I think that was stimulating some of the interest, which was great. So that was what I wanted to show this evening, and I'm very happy for any comments anyone would like to make.
Well, excellent work. Did you have to do any RFI mitigation on your data?
As I said, that particular data is is cleaned somewhat for presentation purposes. So I've cleaned off some of the RFI stuff to really demonstrate. So it's not as clean as that looks, I'll admit.
Did the difference in amplitude coming into ezRA for the different antennas have any noticeable effect when you combine them all together?
In what way?
Well, you get one antenna, you get a smaller gain coming in, so your heights are different, your amplitudes are different in the data, and then when you combine that with another one which has maybe a little more gain, you get higher peaks. And then so I don't know if that, when you threw them all together, whether that had an effect or not.
I literally just threw it all together. I mean, I hope Ted will make a comment in a second now, and I'm very happy, Ted, for you to make a negative comment about it. That's not going to offend me in any way at all, because I literally just took you know the intermediate files, the ezB files and the npz files that are produced as a result of the EasyCon analysis. So for those people who don't use ezRA, the first piece of software that you run is a Python program called EasyCon, which does the initial processing exercise, and that then produces the intermediate files called which have a suffix npz or ezB. What I did was I ran that particular piece of software independently on the 3 telescopes, which produced the intermediate files quite happily. And then I stuck all those intermediate files together in a single directory and ran things like EasySky and EasyGal, which are the ones that produce the various plots, and an EasyPlot just with the entire lot of those npz and ezB files all in the same directory, and it just happily churned out a load of plots at the end.
Nice.
The question is whether they are valid. I mean, that's the question. They seem to produce nice plots, and they seem to look good, but it doesn't necessarily make them valid.
I will say that ezRA does love to make plots. Yeah. It just chews on data and spits them out in all kinds of pretty colors. I have the same question as Rich brought up, that the different, well, let me say it this way. ezRA assumes that your measurement system remains consistent through your measurements. And I've proven that that's maybe not quite right. I've seen problems with different seasons. So indeed, I put some plots in the end of probably Easy Plot up at the high numbers that look at it versus your calendar date. You know, is there some correlation between temperature, for example, and the intensity measurements you've gotten? This is the limitation, that ezRA isn't actually calibrated to a known standard in any way in units. It's just kind of assuming relative measurements between all of these measurements. So yeah, if you have a different system collecting data and you glue the data from another system that's collecting data, are they having the same system gain, and do they talk to each other? So I'm interested in your Easy Sky 100 plot to see if there's a dramatic variance between those things. And it could be that they're all mixed. Well, I guess no. They're probably in order because they get sorted by pretty much file name first. So that's a possibility.
The one
But
you're
this
looking
is a
for.
good discussion for after this meeting.
Oh,
But
okay, we'll
these
come back to
are
it
the
afterwards.
concerns.
Yeah, okay. Sure.
Okay. Excellent work. All right. Let's do Abel.
Hello, everybody. Let me share some slides if I can.
Go ahead.
Almost. I think I got it. You see my slides?
Yep, there it is. Wow.
Yes. Okay. So last meeting, I was telling you our Arecibo project. I will go quickly with that. This is a project to search for transient radio signals inspired by the WOW signal. And everybody knows this page with the WOW signal right there. And last year, we saw this by observing a totally different region. This is data with the Arecibo Observatory taken in 2019, I believe. And you can see here in the middle, these stripes that look like these are in the vertical axis is the frequency, and you can see at the top the profile of the hydrogen profile, but within the profile you can see these stripes, which are small hydrogen clouds, and that look like a narrowband signals, and like the WOW signal, and that gets an idea that maybe the WOW signal is somehow related to these narrowband signals from hydrogen clouds. But the problem is that these signals are constant for decades, and the WOW signal was a transient event. So we invoke one way for this in theory, but one way that these clouds could be excited and emit a beam of energy through like a maser flare or a super radiance event. And once we got this paper last year, the new thing is that Ohio State University SETI team provided us with all the data. So all that page that you saw, the WOW signal, is not the only one. There are about 75,000 of those pages, and we have that data. And we have been in the last year reading that data, and we have a few surprises. So this is the new things that we just put together a paper last this August. So we have a new position, new coordinates for the WOW signal. These are gray boxes here, and the coordinates below are the previous known location. But since we have the data from that days and the month before and month after, we were able to track some sources, astronomical sources there, and compare with current coordinates and calibrate all that data. So we now have two potential regions as before, but they are narrow. They are offset and also narrower. So we are looking through these regions for potential sources related to these clouds, or actually any other source, not only our idea, but also any potential sources. And we requested new telescope time, just to observe this region is more detailed in the near future. So that's one of the results. We also recalibrated and fit the way the WOW data, also getting new constraints on the position, but also we use this to estimate the signal compared into the actual signal in flux density. And I will tell you that a little bit more about that. We found signals like the one that I show you in Arecibo, but with the big ear telescope, the one that detected the WOW signal. And here you can see narrow band signals like this one. This goes to 2.5 up to 5, not to 30 like the Webb signal. But this is the following the big pattern. And when we put the coordinates, you can see that that's related to small hydrogen cloud region. And also there's another, and we call this region WOW2, but this is a cloud, a hydrogen cloud. And there's another one here. And you can see here the pattern also. There's a narrow band signal due to these clouds. This is weaker, but it's also makes a narrow band signal. And because we were able also to constrain the frequency of the Webb signal is not related to the big hydrogen profile in galactic, it's some other region at different speed. And this is that region, but the current resolution that we have for these hydrogen lines in this that velocity is not that good. So we will do more observation to see if there is some hidden clouds here or intensity. At least there is one in the middle, but it has to be in any of these two regions. So we need more sensitivity, and that's why we're requesting big telescope time. So in summary, we have that we also did an analysis to try to check now that we have more information, more data, if some explanation with radio frequency interference, external or internal. We didn't find any explanation at all like that, so that's good. We have the new location that I told you about. We have a new intensity about 4 times higher than the most commonly cited value. So that was a strong event, so strong that it is almost detectable by small telescopes. We also have the new frequency, which is related to the speed that I told you about, and that similar signals have been detected, but these are confirmed small hydrogen clouds, and that gives some support. But it's not the final nail to say that the Webb signal was definitely due to that emission from the cloud, but at least this is an explanation that fits every detail so far. Just to tell something else, unrelated, but we received Observatory 12-meter telescope. That was the only other radio telescope in that in the field site that has been there since 2011, is now is getting setting up for being used for education and science, maybe by the end of the year or starting next year. So that will be some additional instrument that we will have also, but for targeting observations in radio astronomy. So thank you. Do you have any questions?
Yeah, I've got one. Since the frequency is so close to what we use for the hydrogen line, and we've got people with tracking dishes, and we got people doing drift scans. If we start looking at those right ascension declinations at that frequency, what are we looking for that would tell us that we got it?
Yes, that's an important question. That's exactly what we're addressing. So because we have a new location and a new frequency, it's like starting over again for people that want to search for the signal of the source. I don't think that is wise to search for the signal again. We think this is a event that once you have that cloud, have the emission, it just alters the cloud, and it's very unlikely to have it again. It takes time to build up. So maybe these events are in different clouds everywhere, but it could be much lower than once per day. So very difficult to detect. So more wise it will be to detect the source like these clouds. So that's one way to do it. If you look at these locations and, for example, look for objects having this speed related to that frequency. That could be something unrelated, like stars. There are stars in that region that have this particular speed, not that many, but there are stars. So if that's related to that, there are hydrogen clouds in that region also. That so it narrows down not only on space but also in frequency. Because, for example, if you find out that it was something speed close to the all galactic things in that area, there are many objects to select for. Now we have narrowed. It doesn't mean that all the previous 10 missed this area because they were wider and included this area. Probably in the terms of frequency, it might be better. The analysis will be different. And in terms of the location, you will be more specific to that location. So maybe that will make a difference to identify the clouds that are responsible or any other object unrelated to that. Mm-hmm.
Okay. Any other questions for Dr. Mendez? This is great stuff. I'm glad you're letting the group in on the these new advances in the WOW signal. I think it's just that's kind of stuff everybody likes. And okay, thank you very much. And Ted, what do you got?
I wish I was busier with radio astronomy. I've been distracted with optical stuff. Let's see, I'll show you just a pretty picture.
Okay, Ted, nothing's come. It looked like it was started to come up, but it's not up yet. Oh, there it is. Wow.
Okay, I finally got my mute on too. Yeah, so we built this observatory out in a kind of an empty field, which is good. The wind does blow up there too, but that's fine. But it's fairly close to us. And we got the dome, we got the pier, and so now we're finally getting the mountain, and the telescope came in soon after it. So that's been a distraction. And now I'm supposed to be doing lots of Arduinos to control servo motors. So I've been distracted. But in the meantime, radio astronomy, I've been trying to get an SDR play working, and I can't get SDR play to see anything at 1420 with my home telescopes. Now, Rick here with his 60-foot dish got some response, but it's terribly weak. And we just don't know if it's our problem or the SDR Play's problem. So if anyone has results from SDR Play that were successes at 1420 megahertz, I want to hear you. It works fine down at 100 megahertz. That's not the problem. But way up at 1420, I think it's just kind of deaf SDR Play, at least the one I have. And then I'm working also for number 3 is talking about Estes Park, where I have a small dish, scope in a box kind of dish, and making a whole bunch of new measurements. And so having fun with that. I think that will do it. Back to Rich.
All right, thanks. Any questions? How are you powering that? Is it all solar?
We have AC power underground over to it because of all the trenching that we had to do. We also have fiber optics. The concept is to be a remote optical observatory where we sit in our living rooms and push buttons to make it work all night. So we
Nice.
think that's a fine idea. They do this course down to places like New Mexico and Arizona, where the skies are nice and clear. And we ought to learn how to do that too, so we can teach our kids.
Great. I think go put a scope in the box antenna, on top of the optical one, so you track the same. Anyway,
Yeah, sort of. It's been brought up. I want to put meteor cameras out there too.
yeah. Okay. All right. Thanks, Ted, and thank again for ezRA. I mean, even though it's keeping me awake at night. Rick, are you ready to show something?
Yes, yes. I'm working on some PC board problems with my spectrum analyzer, as you've been speaking. Some of us went down to Haswell to work on two different projects, the E-Callisto project and the drift scan project last week. And the problems that Ted just mentioned were I had changed out the hardware from a low end receiver and some different amplifiers, changed all the hardware to the SDR Play RSP Duo, and we were going to try to do some interesting experiments because that has two receivers in it. So I put a 3 dB splitter in front and fed both inputs with the same thing. And our plan was to run two different analysis programs simultaneously, one on each channel, so that we can compare the results. But we didn't have the software ready for that, so we just set up ezRA and collected data. And as you heard, we got response, but not the kind of response you would expect from the dish we have. And so I've swapped out the data collection software remotely from here with a newly created data collection, also using GNU radio modules, but a totally different design. And the output of that is designed for the Virgo spectrometer software that Dan uses for pulsars and other things. So I collected about a day's worth of data and sent it to Dan, but I know Dan's unavailable this weekend, so I do not have a result. But we're hoping that whatever result we get from that data collection, which is the same exact hardware that we used for ezRA, but totally, completely different software design for collection and filtering, we should learn something about whether the problem we were seeing with ezRA is hardware related or not. So by next week, I should know the answers to that. Let's see. What else? Okay. The other thing I plan to do on a trip down there that I will be taking soon is I'm going to replace all of the hardware again with different gain blocks, and I think I'm just going to go all out, and I've got a spare B210 receiver, which is considered to be way overkill by some people for hydrogen line drift scan measurements, but what the hell, I've got it. I'm not using it right now, so I may put that in there, and that should put to rest once and for all whether we're having hardware problems currently with the SDR Play hardware or not. So we'll see, because I'm pretty sure that the interfaces, the GNU radio interfaces to B210 are pretty well understood and working. So that's my next plan, is just to throw the most capable hardware I have available at the problem, because we'd sort of like to get past this and actually start collecting data. And given that we only go down there every few weeks, once I have a system that I know is going to collect good data and produce good results, then we have to go through from plus 20 to minus 20 degrees in 1 degree increments to get a full map. And that could take, as I told Ray, that could take 2 years because we don't go down there very often and we're not permitted to steer the antenna remotely at this time for safety reasons. So that's where we are. We're still not quite, we're getting data, but it isn't what I was hoping for. So we're still working on the design. That's it.
All right. Any questions for Rick?
Yeah,
right.
this is Ed.
Go ahead.
This is Adrian. I have a quick question on the SDR play. Could that be done on the bench and then just using a signal generator attempt to plot out what the actual sensitivity of the receivers are at 1420?
Well,
And not just guess.
It's a funny thing you asked that question. Yes, when I get it back, I have just received, I had sold all my signal generators when I moved out here to Colorado, and I didn't have one appropriate for this anyway. So I just purchased a high-end Agilent single generator, which would do that job nicely. It's remotable, it's got Ethernet for control, and it's a vector signal generator, so I can put IQ in it and produce any waveforms I want. So I finally got the signal generator I've always dreamed of, but it just arrived last week. So I haven't been able to test it, and now I'm waiting for, once I swap out with the B210, I'll bring that home and I will make some of those tests. But my suspicion is it's not the hardware. My suspicion is it's the SOPI driver for the new radio that is designed for that hardware, because when I change the RF gain parameter in that in that for that module, I get no change whatsoever in the RF output or in the output levels as viewed on the GNU radio spectrum analyzer module. So I'm thinking that there's a problem with the SOPI module, but it could be any of the other modules along the way. They haven't been fully vetted to be sure that all of the math from one module to the others has the proper gain factors and dynamic range, is make sure no dynamic range is lost and all that stuff. So there's a lot to do in just evaluating our data collection software modules in GNU Radio.
So I proved my antennas are working here in my backyard, and I ran the Linux version of SDR Play's receiver software. I forget the name of it at this point. There are two of them. One of them is Windows and one of them is Windows Linux. So the Linux version, and it couldn't see anything at 1420 either. It saw things just fine at 100 megahertz. So the hardware was working, but maybe not at 1420. So one more data point. This will continue. Our exploration will continue.
Are these observations being carried out with soldered LNA front ends, or just straight into the SDR?
Oh dear, no.
I have an LNA, the Sawbird LNA at the antenna. Yeah, and I've proven the signal works just fine with the RTL SDR, simple SDRs. So
Yeah, we have a good LNA at the feed, and last week we were able to get very strong signals from a new pulsar at 20 millijanskis. So I'm pretty sure the preamp is working.
It's fine. All right. Thanks, Rick. And by the way, I got this for 40 bucks. It goes to 1420 megahertz. And the only dilemma you've got is that when I turned it on, my backyard telescope picked it up, and it just blew all my observations away because it's so strong, and it goes down to 40 megahertz, but it's like 40 bucks. And so if you guys need an SD, if you need a signal generator, that does it. Just got to be careful. Put a lot of attenuation on it before you turn it on.
What make is that, Rich?
What's that?
What make is it? Where do we find this?
I will put that in the chat. I have to go. It's on Amazon.com, and I'll put a link down there as soon as we let someone else talk here for a second, and I'll get the link.
Thank you.
Okay, let's get our Robert Lucas. And are you in Australia? He could be anywhere in the world. So I'm not quite sure where he's at now.
Well, I've just been out, trying to, photograph the total lunar eclipse here from Sydney. It's the middle of the night, remember? And I lost. The clouds won. So what have I been doing? Well, Ted convinced me to, redo the ezRA, and I've been doing 3 days of, of scans of the Milky Way. I've, started, just about at the southern pole, and I've been working my way up at, 5 degrees per 3-day scans. And I've collected a bunch of data, but I haven't done any processing. 2 weeks from now, I'll be on the plane to New Zealand. I'm going to Christchurch. There's a partial solar eclipse that I'll be able to see from Christchurch. So I'll be doing that. And then I'll be back for 1 day, and then I'll be off to the States again for a month. So outside of that, waiting for my feet to touch the ground.
All right. Thanks very much. And yeah, this is I got the, let me see if I can share my screen here. Not too many screens up. Let's see. Oh boy. Okay. For anybody who wants this thing, it's called a Max 2870 RF signal generator, 69 bucks on Amazon. And it's very good. It does sweep functions. It does steady things. It has a 20 megahertz output for calibration, and it's 69 bucks. So if you need a signal generator that does 1420, this is it. I think it goes to 6 gig. This thing goes to 6 gigahertz. This signal generator.
Rich, we think we've lost your video.
Yes. I'm trying to I was trying to get that just a minute. Let me see if I can get.
We want you back.
Can you hear me?
We hear you fine.
Okay.
Your video is blank.
Yep. Let me put a
Confuses us, but all right. Maybe we don't need to see you.
all right. Let me try something here.
And not even your name shows up. So you seem to be giving live video, but it's black.
I know, because I'm trying to select something and it's not letting me.
Anyway, but
anyway.
Thank you for the input. That's good. We'll go take a look.
Yeah.
Sorry guys, I'm having a look on Amazon here in the UK, and I'm coming up with a whole range of ones that all claim to be the same, but the price range is phenomenal, from £46, including a little screen, up to £111, and I can't really quite work out whether there's any difference, or how do I know if there's a difference?
All right, you see
That's-
this?
That's
You see
why
the
we're so
screen now?
eager to get Rich's version.
You guys see this one?
No, we see no video from you. It's turned off.
I can see you. I can see your video, yeah.
Okay.
Yeah, I can see you too.
I
Okay.
see it too.
Just me. Sorry. We see the sharing.
Yeah. So you should see the.
Somehow with me on it.
So you see the Max 2870 picture with Ted's picture on it.
Yeah.
And so we want that URL in the chat if you could.
That's a. I could do that.
Oh, well, I see. It's a slide, so we'll have to copy it.
That's a slide, but I can, and it's an Amazon. It's on Amazon, so, and it's got that big long URL. So I don't know if that does you any good. Anyway, so if you find that, I've actually got this is my second one I've got, and it works great. And so USB powered. I'm saying it works too well. If you got to be careful with it. It'll jam your your hydrogen radio telescope. It's so good. Okay, let me stop sharing. And
So Rich,
go ahead.
Rich, does that have a variable attenuation on the output, or is it just one single?
Yes.
Power
Yeah,
output?
it has a I think it goes down to -4 dBm and it goes up to 1 or 2 dBm. So it is variable, but I would, before I'd use it on anything, I would put some inline SMA attenuators on it, because it is pretty strong. If you hook it directly up to something, you're gonna you probably want some attenuation on it first. I had every attenuator I own, a big long streak, and my mute's off, my picture's off here. Let's see. There I go. Okay, yeah, I had a big long. I had to stack that long with attenuators on to run it into my RTL SDR. And it definitely works. Okay.
Hey, can I make a comment on several of those signal generators I've played with in the past? The problems have been shielding that, there's signal coming off of the board itself. So if you have a circuit board that's open that you're working with, it's not real well shielded, neither is a generator. And attenuators may not matter because it's from the circuitry in the signal generator to what you're testing, and it can run you nuts, kind of thing.
Right.
The reason signal generators cost a lot is the shielding. You get to the, $5,000, $10,000 signal generators. You look at the shielding on them there, and half the cost has got to be in shielding.
Yeah, but we're amateurs. We like no shielding, and my 9-foot dish, which is 100 feet away in the backyard, picked it up with that little antenna on it. It picked it up full blast. Okay, let's keep going. Pablo.
Hi, can you hear me?
Yeah.
All right. I have a question as far as using different dishes in visual observations with the AAVSO, the American Association of Variable Star Observers. We use a transformation coefficient. Basically, each observer calculates the coefficient for their telescope and detectors, and these coefficients describe how your instrument differs from the standard system. Couldn't we come up with some sort of an arbitrary standard system and then come up with a coefficient that we can all use in different systems, and so we can either do it within an observatory with many dishes, or just all of us, and be able to transform our readings and be able to build a global picture of whatever we're trying to detect.
I like
words,
that idea. My concern is that even during the day, my system gain will jump up and down much less from day to night. And so which number do you choose, you know? Now
Well,
you've
we
got to
choose
get
a
a
day.
graph.
We choose a day or night coefficient, rain, clouds, whatever, and then we apply that. And with artificial intelligence, you don't have to be a PhD to do it. I mean, I can do a prompt with a picture and ask them to do it. So we could design a coefficient or a set of transformation coefficients here that we can all apply to our different systems, maybe with a little program that we can supply to everyone, thus be able to normalize all of our readings and build a global map of whatever we're trying to
Right.
detect.
Would TSYS work for a standard
What is that?
system temperature TSYS? Because we all learned how to do TSYS on our telescopes, and that's really the that describes your telescope. Now, that would
Yeah, that would be
basically
a
allow-
that would be a parameter. It could be a set of different parameters, just like Ted said, day, night, rain, whatever, temperatures. We could probably build a program using AI to take all these things into account and say, okay, Rich Russell's telescope, it's going to be the standard today, and then we're all going to transform our data to correspond to Rich's standard.
Well, I think we could probably we probably want to see if we can get a professional standard, and I would go with Wolfgang's antenna, because I think he's actually done calibrated runs that are, you know, transferable across the professional realm. And so we start with that, and we compare, everything compares to his. I think that would be an approach. But I think, yeah, he starts with his TSYS, and then he uses that in his when he does calibration. Anyway, excellent idea. I think calibration is something that the amateur groups really need to start thinking about, but we haven't delved into that yet.
And the reason I've been thinking about that is because I've been playing with the Discovery dishes. And can I share something here?
Go ahead.
Screen 3. Okay, this is a live video of side of the house. This is the one that I use for radio astronomy right now. It's on the roof to the zenith. This one here, it's the GOES 18, so that I can get weather live. And they're all feeding into 2 different RTL SDRs into a 15-year-old computer, and it's working great. Let me stop share. Oh, come on. My computer almost, okay. And then let me share again. Just, let's see, screen 4. I got too many screens. Okay, and this is a video, a Chrono Lapse video of course, this is the GOES 18, and this is the H-line. Let's see if it works. And you can see that it starts detecting even the gas even before it gets there. Pretty sensitive. So I've been stress testing these dishes in 105-degree temperature out in the sun, and no problems. I haven't tried it. Anyway, enough of that.
How much do they cost again?
The LNAs are amazing. I mean, you saw they detect gas with a 70-centimeter dish, even when it's not even close to, well, the beam width is very wide, but even in the middle, it'll start detecting hydrogen, meaning that the LNAs are very, very, very sensitive and well-tuned. I think the total thing, the LNA and the dish total is like $235 delivered. Let me stop that. So I'm thinking of buying a couple more and trying to stack the data that I get, which is something that I posted on the website that we can do, and or just about everybody here could afford for 235 that includes the LNA, perfectly tuned LNA, and so you can have a smaller radio telescope for about $235. And then we can gather all that information, transform that the data, and get everybody to participate globally. Anyway, that's all I can have to offer at this point. Oh, I've been working with. I'm going to, of course, going to work with the ezRA radio astronomy, and I've also been working with Chris in his project H-Line 3D. Just experimenting with that. But I do have two other dishes. One, it's a 3 meter, one, it's a 2 meter in the backyard that I'm planning on activating and see if I can transform the data so that I can add it up and see if I can get something, I don't know, from the WOWS signal all the way to a maser. That's it. Thank you.
Okay. Hey, Ted, I've lost control of my Zoom here. So you need to go ahead and ask for somebody else. I have to figure out what my screen.
Gosh, let's see. We got down to, I think you're just doing alphabetical here. Oh,
Sorta.
no, Pablo's down near the bottom. All right, so I'm going to start alphabetical. Adrian, have we heard from you yet? Please tell us what you're doing.
Hi. Well, I've been on and asked a couple of questions. No radio astronomy in here. I'm still trying to recover from a massive problem that I had where I had a computer that was totally wiped out by a Windows 11 update. And this has been kind of a general update phenomenon that has impacted quite a number of computers. I can put on the chat some references and even YouTube videos of people discussing this. But apparently, what this update did, it kind of scrambled the SSDs on multiple different systems, and it seemed to impact especially SSDs that they're somewhat on the lower end. There's some other criteria that they said contributed to the problem, but the lower end SSDs have utilization of what they call kind of a buffer when you're writing into them that utilizes some of the system memory, and then somewhat higher SSDs have they call it on the higher end SSDs they actually have an onboard DRAM, which is actually what's used for the buffering, and these seem to have resisted the impact of the Windows 11 update. So I'm still trying to recover some of the data out of the computer, the laptop. They got wiped. I had to buy an external reader for the SSD that was in there, and I bought a new SSD. So I'm attempting now to reload Windows and whatnot on it. So that's kind of a long process. But yeah, so that's kind of been a kind of a clincher. I'll put on the chat some of these references if anybody's interested. But I'd be kind of wary on Windows 11 with updates. I know there's some software out there that can be used to block some of their updates, but you might consider that. As I said, I put some of those links on the chat in case anybody's interested in looking at them. Or upgrade the SSD on your computers to somewhat higher end. Look for one that have the onboard DRAM rather than the ones that utilize the system memory for the buffering. That seems to have been one criteria that helped in preventing this problem. so far Microsoft hasn't really owned up to it. They said that they tried to study it and can't reproduce it, but there's numerous people online that reported their computers just totally wiped. Some temporarily, they were able to regain the computer being able to see their SSD after a couple of power cycles. But anyway, that's kind of been what's preoccupying me for some time. I also want to add maybe on the chat another signal generator. I've got two of these. It's called the Morpheus, which is kind of a fairly nice unit. It actually has other multiple uses. It has a built-in mixer, so you can almost use this as a converter. And it also goes, I believe, up to around 5 or 6 gigahertz, and that's seems to be a very clean signal output from this signal generator, and it does have quite a bit of attenuation software, sort of power attenuation that you can go down quite a bit. I have not tested it directly with hydrogen line reception, but with just reception at other frequencies. For example, some of the kind of distant ham beacons at various frequencies that I've used the signal generator to sort of compare the signal from the microwave beacons, and then try to sort of compare what the output from the signal generator is. And it's a little bit more expensive, I believe, than the one that Rich presented there. But like I said, it seems to be a fairly good unit. I can't recall exactly what I paid for it, but it might be running more like, or maybe twice as much as the one he's referencing there from Amazon. But in any case, I'll put that link on the line now in case anybody's interested in looking at that. And so that's about all I've got to say. And hopefully I can recover some of my data that I had on the laptop and get back to trying to do some radio astronomy at some point. Anyway, that's about what I've got to say.
Very good, Adrian. Keep us informed. Give us those links. That's always helpful. And hope you come back to the land of computers. Sounds good. I'm working my way alphabetically down the list. Rich now.
I'm back, and I've got a presentation. If
I call upon Rich to give a presentation.
All right. This has been a big controversy. Not a controversy online, is can we do a phased array? And everybody see that?
Yes.
Okay. So the difference in the interferometers and the phased array is that the interferometer is relying on the when an object passes, it's actually the signals are causing a fringe pattern, which is causing a more steep signal. On a phased array, just like radio Jove, it's causing the beam to actually steer. And the meridian, my concept of a meridian phased array is that the beam's going to be steering in declination only, and we're going to cause the back antenna to line up phase-wise with the signal from the front antenna. So both of them would be looking straight up, but the back antenna will line up and cause the beam to change declination up or down.
I'm still looking at page 1. That's correct?
Yeah, that's good.
Okay, good.
Okay, so first, so sort of the status. First, I had to get ezRA back up online, and I got it up online with my 9-foot dish, and my 9-foot dish in the backyard, thanks to DSCS. I've had this thing for, this is what I initially started hydrogen on, and in the backyard, and using Excel to map this stuff. So so ezRA is a dramatic change from using manually doing that with a Spectre Cyber. So I've been able to do that, and I'll show you some of those pictures of the my 9-foot dish with the ezRA. I've assembled a 2-channel phased array system, and that's the using the RF phase, and I'll show you what those the hardware is for that. I have an Excel program to calculate. Now that each phase, RF phase board has 8 bits where you program the phase angle into. And because of that, I had to get an Arduino to actually put those 8 bits, set those 8 bits, and then and then have a reader read those. So I've got that all worked out, and I use Excel to sort of calculate what the 8 bits are supposed to be for any phase angle. And I'm currently running it with one antenna. My goal was I need to basically, and it's a scope in the box antenna. I need to be able to get all this stuff working with one antenna looking straight up, just to prove that it can see it. And I'm now in that point of the project. I'm not having a lot of success. I don't have the antenna in the right spot, I think, and I'm too close to the house. Various other things, and I am using an RTL SDR. And to note is that I'm not using an LNA. I'm not using the LNA powered by the SDR, because once you start adding antennas, you can't have power running over the line. So I'm using externally powered, in fact, a battery powered one now. So I'll show you some of the results here. This is the results from the 9-foot dish so far, and looks pretty good. I haven't started the RFI mitigation, but I think that this is well on its way to doing well. And notice I haven't got a lot of lines yet, but I'm working on that. So I'm happy with that. So the meridian phased array, the basic concept is, this is a scope in the box antenna. This is a Wi-Fi antenna, a Yagi antenna. I've got both of these things, and I've got 2 of these Wi-Fi Yagi antennas. My thought was that if I put those things all in a row, north to south, at 1 or 2 wavelengths apart, 0.21 centimeters is a wavelength, then I'll be able to use that, and they're relatively cheap. They're about $30 each. And I tried that once, and it didn't work. I don't think I had enough gain, so I went back, and right now I'm running with a scope in the box and dish, and trying to see if I can get that working. And then when I get that one working, I'm going to get another one of those and then have that go in as the second beam or second antenna. I found these battery powered LNAs because I can't have the LNA powered by the SDR. One thing that I'm running through an RF phaser right here. This is an RF digital phase shifter. It has 8 bits that control it, and you run an LE. You cycle that LE from you load the phase number by making the LE low, and then you cycle it high to low again, and that sets the phase angle in that phaser. So I'm going to have both of those. The front one, so the southern antenna would be always looking up, and then the back antenna will be the one that'll be phased. Then I got a splitter, and then a standard RTL SDR, and then windows. Note when I ran it the other night, and this has only been within the last couple of weeks here, so I'm still having startup problems. The batteries died in these guys overnight. So one thing I'm going to do is, for $6, you can get these 12-volt powered 30 dB LNAs. So that's another external LNA that you can get by just putting 12 volts on, and it's more powerful than most LNAs. So think about that you don't have to have the current LNAs we've been running with. You can get a cheaper one, just have to provide 12 volts to it, and you've got a very powerful LNA there. So I'd put those in place of these, and then put external 12 volts to them. This, in fact, is what I've got on my 9-foot dish, which is 100 feet away from the house. I've got these guys, and I run 12 volts out to that, and that's what powers the LNAs. anyway, that's the basic design. This is the RF digital phase shifter, also $30. So the concept here is that once I get this running with two of them, and I prove out the steering, etc., then I can add as many as I want after that. Because even though I'm sorry, I actually had an Arduino here too that's doing this. The Arduino can actually just, I'm not limited by the number of ports here because I can have all of these ports talking to the same bus, and then I could just change the LE for the different RF. And as long as I keep a high signal on +5 volts on the LE I don't want shifted, and I cycle the other one, I can just vary the bus digital for each one of those things, and then just control it with that LE thing. So I can have multiple, up to 20 or 30 of these things in parallel. So I don't know if that's possible, but that's my thinking, is I can keep adding these things and increasing the gain and using the phase shift technology there. This is the some of the outputs of this digital phase shifter. It's a 1 to 2.2 gigahertz phase shifting. Pretty cheap, and if it works, then it takes into account all this stuff. We don't need any. People are talking about patents and all that kind of stuff. This is all straightforward stuff. As soon as you can get the prove that it works, that it shifts properly, and you can actually beam steer it properly, then you can just add these things to your heart's content on that. So that's my goal here. The steering angle is all dependent on the distance between the elements, the antennas. So this is the formula you use for that. And if you plug that in, the question is, how do I do that? My goal is I want to be able to plug in Arduino. I want to be able to plug in the elevation angle and get the have it come up with the phase, this delta phase number here, so that it'll automatically then have that put into 8 bits, so that I can have that Arduino automatically put that into the RF phase shifter. So I built an Excel program that takes into account speed of light, wavelength, distance between antennas. This is like 2 wavelengths right here. The electrical angle. So basically, you put in the elevation, and notice I have latitude and declination plugged in here. So with this thing, I can put in the elevation I want. It goes through the calculation. It determines the phase offset degrees. And then since this thing is actually, since it has 256 bytes or bits, 256, it goes up to 256 with 8 bits. That's approximately 1.4 degrees is the finest I can get it. So if you do that number, you can actually calculate the bits that you need to plug into the RF phase shifter to get the 10.88 degrees phase shifting. So that's very straightforward program with that calculation. This is an example of what I'm actually running right now on that one dish. Notice I have 90 degrees here. I have it pointed straight up, and I'm running it. My biggest problem here is, you see this, and Ted probably can recognize this. You see this thing here is because those battery powered LNAs aren't reliable. That's why I'm thinking about getting the other one. And you notice that this one dropped, and then you can see it trying to come back on a couple times, and then it came back on again. So I don't consider them too reliable right now, and so I'm going to try to shift those to a dedicated 12 volt. And I use the one I have on my big dish. I use a ham radio 12 volt power supply, and so I'm going to do the same thing with us and get those new ones. This is what I've currently been doing. So I don't see at this point here, I'm not seeing any signal, but I haven't done any RFI mitigation yet on them. So, you notice I've only gotten very short periods, and most of that has been having LNA problems. That's an example of what happens when the LNA drops. That's one LNA. I have two of them on there now, and one LNA dropped. And by the way, that RFI or that RF phaser has a 20 dB gain to it too, so that's also considered an LNA. And I also may have a steering problem. I'm looking straight up, but what signal I did get, max signal, is above where it should be. So I might be pointing down here to line that. If I line that up, I might be pointing down here instead of, at 90 degrees. So I have to still consider that that's a problem with my setup. Okay, so next steps. I need to get the single channel, which is basically I have all of the right components, the phasers and everything like that in line. I want to get one dish working. That'll be the scope in the box antenna. And when I get that one working, then I'll get the second scope in the box antenna working on the other phase channel and get that to show something. Right now I need to get a better cable. I've got a dinky little cable. It's probably too small, and I'm probably too close to the house, so I need to move everything away and power up my LNA separately, so I don't have this LNA dropping problem. Then run two antennas at 90 degrees elevation, and see if I can get my pointing correctly. And then I start phasing, changing the phase angle and running it through ezRA and seeing if I can actually line up the beam with the galaxy. And long term is I add a third antenna and a fourth antenna, all in north south. So the big picture, why do this at all when you can just use a tracking dish and just even my 9-foot is I can move it up and down and declination. Here I can actually, and Ted says that it's possible with ezRA, is that I can actually electronically go to each degree as small as I want to the in declination and say move it every 10 seconds, which I think is the integration time. Every 10 seconds, move it another degree, and then just keep working my way up and down electronically and taking observations. And then, talking to Ted is very possible. And I'm doing that with the Arduino, having that Arduino actually tell the ezRA what the declination it's currently pointing at is. And then ezRA would just do all the calculations. And at this point, in one day, I can run the entire sky using this method. So, and then just by adding more antennas, I get more gain, potentially a tighter beam. So I can maybe rival some of the big dish antennas in terms of the beam. So that's the goal. And any questions?
Yes. Hi, my name's Andre Powell. I'm actually just outside Cambridge, in the UK. First, thank you ever so much, everyone, for inviting me to this, and it's lovely to hear you, ladies and gentlemen, talking about your stuff. I'm literally just getting into this. I did back in the COVID days actually create a horn for looking for stuff, to actually then using a spectrum analyzer to try to track stuff. So, but what I'm now trying to get back into stuff doing properly with an SDR type stuff. The SDRs I have are SDR plays, also a Neuralink. It's the one which actually has the broader frequency. So I didn't actually realize the fact there was a thing called a scope in a box. I happen to have one of those antennas set up outside my house, and I intend to actually then have another one to try to do the do a phased array thing. So listening to you, Rich, saying about this actual phased board is absolutely brilliant, because I was just been thinking, how on earth do I actually do that? I've got several Arduinos, and so that's absolutely great to know the fact that that's one of the solutions for that. So, so it's just fantastic to know that somebody else is doing the same kind of thing that I want to do. I mean, I design silicon chips, so I know a little bit about electronics. So it's actually good to hear this kind of stuff. So, also, I've been in contact with Newelec. Apparently, their H1 Sawbird thing will possibly come on back and sell in about a couple of months' time.
Well, if you want to do phasing, I would steer away from the Sawbird, only because it's powered by the cable and the RTL SDR. And in fact, what Ted had to do, what I had to do in ezRA, Ted found a command to turn off the bias power on the RTL SDR in ezRA. So I had to enter that first, because I didn't want power going back to the cable. And so at that point, you need a different kind of an LNA that is externally powered.
Yep.
Right.
Yep.
If you want to start combining those, and if you've already got an antenna now, the microwave or the Wi-Fi antenna we use for scope in the box, purely a starter kit. It was meant for 24 Wi-Fi signals, not for 1.4 gigahertz, but it works. And so if you start looking at the more advanced ones, which is the disk Yagis that Alex has put together, Ted's even put some Yagis together to do interferometry at 1.4 gigahertz. So there's all sorts of ways. If you go to Andrew's site, he's put all sorts of antennas together for hydrogen. I would start with get on ezRA on your computer, get an RTL SDR, $12.
Yep.
Starting with that, get an LNA. If you can't get a Sawbird, get a different one. I mean, even the one I've got is $30 for a battery powered one that you could put out there. I just don't trust it for any long term observations, but or get a separately powered one, and you're there. I mean,
Yeah,
and then you start take observations. Then you start worrying about this RF phasing stuff, because that is causing me all sorts of trouble that I don't have with even my big dish. So
I totally understand. I mean, first, I want to get the system up and running. So the fact that just one antenna, no phased array type stuff, literally, capture the hydrogen line, and then I can say that, okay, now I have a proof of concept. The fact that I've actually got the system starting up in this respect, and then after that got that point, I can expand off. What also I've been doing is the fact that I've been actually 3D printing a dish, so the fact that I can have multiple dishes and like that. So it's all very, very exciting as far as I'm concerned.
If you 3D print a dish, there's this RF fabric you might want to consider. And I don't know if anybody's got the link to the RF the fabric that people are using to line their dishes with. That's great reflector. That might be, you might use that for your dish, your 3D printed dish.
Rich, I'm a little worried about time.
Oh,
okay,
sorry. I'm sorry, guys.
Dimitri has a question, and also Preston has a presentation.
Go ahead, Dimitri.
Thanks, guys.
Thank you. Just now I'm tracking the eclipsing moon by my 43 gigahertz telescope. You can see now it's coming of full eclipse, and begin shining, and I can see how this rate through to cold sky is a bit rising from a full eclipse phase. This is just now happening.
That's pretty
Thank
cool. We're
you.
getting a live
That is
lunar
nice.
eclipse report from Russia. Neat. Thank you.
Thank you.
And Russ is our eclipse expert in the group. So Russ, I think you can count this as observing an eclipse for from Australia. All right,
How
excellent
about
work,
Preston
Dimitri.
and then Dave, I was thinking. Preston, maybe?
Okay, thank you.
Okay. Can you hear me all right?
We hear you nice.
Okay. Let me see what happens when I try to share here. This is just a photo I wanted to show you. It was one I grabbed quickly with my cell phone. And this is Cygnus A and the Milky Way. So any comments on that?
Looks like a Spectre Cyber, is that correct?
Yes. Okay.
Pretty signal.
Thank you. All right, oh, I found out how to share, but not how to stop. I got another thing to talk about real quick.
Cursor up high or low and a window
Stop.
appears.
I see it. There it is. Okay. The other thing I want to talk about, I don't know how many of you just got the latest copy of Physics Today, but there's an article on the Deep Synoptic Array 2000 project in Nevada. And apparently they built several of the trial dishes at Owens Valley. So I found that interesting. And if you get Physics Today, this is a good article to read about it. And those are basically the two things I had. Any questions? Okay. I'm done then.
The question is, why do you get Physics Today?
Oh, I belong to the optical, used to be the Optical Society of America. I used to do a lot of work in fiber optics before I retired. So,
Okay.
So I'm a member. I remember that and the IEEE. So
Wow.
get some good stuff.
Okay. Ted, you want me to keep going?
Dave had a presentation.
Oh, Dave. Okay.
Hey, good day, good evening, good night, wherever we are. I'll be brief. Let me share my screen. So I gave this presentation, I think it was 2 weeks ago at our last call, and I've learned a ton since then. Yeah, on some off time, I came up with this little logo. So I unfortunately learned that this initial layout of antenna was the most horrible layout you could possibly select. So I think I have fixed that. The goals for this very small array were low cost, which it's actually growing. So it's between $1,000 and $2,000 right now. Small angular resolution, that's about half a degree, a little less, 0.4. Use it for imaging, have wide bandwidth. The SDR has 25 meg to 1.7 or something like that, I think. I want to use it for some science. No physical antenna steering. I built an ASL positioner from an Arduino, and it works, but I feel like that's a lot of mechanical complication to have 5 antennas running off of. Another goal was to capture all the IQ data and to process it offline. So there were 5 subsystems. These stayed the same: antenna, receiver, data capture, beamform analysis. I have made lots of changes to the antenna and the beamforming analysis. I did a little, I don't know, about 60, 70 hours with GPT-5. And it is wrong. The disclaimer on the GPT-5 says it can be incorrect. It's very often incorrect. So what I was hoping is that you guys kind of do a sanity check on this. Consider me a farmer. There's no criticism you can offer that will offend me. So if anything in here looks crazy, please say something. I decided to put a ground plane on the turnstile antennas. They're circular polarized. They're about half a wavelength long, and they each have about 5 dB a gain. It's roughly uniform, nice pattern. I'm very sad. I think it was Andrew that said that the Sawbird H1 are no longer available. So I'll have to do some searching for that. I have one on my 1 meter dish right now, and it's worked perfectly. This layout geometry was so important. We had talked about grading lobes because my antennas are farther than half a wavelength apart, and they're up to 120 wavelengths apart. So the grading lobes were awful with a circular geometry. I learned about the UV plane and how important filling that UV plane is for this. So this is the result of thousands of iterations with GPT-5, coarse iterations, and then about 500 fine iterations on each of the top 5 course layouts. This gave me the best UV coverage, minimum side lobe. The peak side lobe level is minus 22.1 dB. The maximum baseline is 25 meters, and the maximum radius from your receiver would be about 15 meters. It has 0.48 degrees of resolution. And let's see what else. The antenna layout supports coherent sampling. Yep. And the other idea I want to implement is if I can get this proof of concept to work with 1.4 gig hydrogen line, I'd like to make other antennas available that the SDR, has such a wide bandwidth that I could just plug and play a different set of antennas into the SMA cable at the end of the run. Point spread function. This is my dirty beam as a result of the optimization that I've done. I don't know if you can see this little tiny red dot in here is the peak, and it's very small. The side lobes are down 22 dB, which to me is wonderful. The Kraken SDR is the SDR that I chose because of the phase coherence. They have an onboard noise generator that they all calculate their phase offsets to, and calibrate and automatically apply that calibration to the IQ data that they generate. So this is the same. This is the same, using Heimdall DAC software to capture the IQ data and to store hours and hours and hours, 400 hours up to in the 80 terabytes of my storage array. After the 60 or 70 hours with GPT-5, which deals mostly with Python, I decided to write my own beamforming software and to integrate between 6 and 12 hours in length, possibly over multiple days. And I do have some attenuation. I have trees. I live in Maine, so I have trees everywhere. I think I missed here, the UV coverage. I wanted to talk about this really quick, and I'm almost done with my slides. So this is a 12-hour plot of UV coverage with my my antenna layout, and you can see that the UV plane. I also wondered, the VLA, the very large array, the opposite of mine, appears really symmetrical, but it turns out that the ellipses that it generates from the Y pattern they're not redundant. They're unique UV traces. So I always wondered why, and I guess it's like a logarithmic spacing or something from the center out, but they are doing the same thing I am, is trying to maximize UV coverage. So let me go back to the analysis. I also did quite a bit in Python, just simulating this setup. In this instance, here's my original synthetic sky. Here's my dirty image with I think it's a 6-hour Earth rotation synthesis here. This is what I get. There's artifacts everywhere, which are to be expected. And this is my cleaned image running a clean deconvolution on the final data. That looks pretty good. The intensities map to the original, and there are some little artifacts here, but I can ignore those. I'm thrilled with this for a couple of $2,000 maybe to be able to do this. Some real-time tools that I'd like to build. I've found out you can, while you're recording the IQ data, you can build a little dashboard. You can do beam steering. You can look at the PSD at the form beam. You can look at each individual channel. I have a waterfall display. You can skip RFI frames. There are all kinds of things you can do with the Kraken during IQ capture. And then I thought of some things as I was working through this design to modularize the antenna subsystems, which I mentioned, include a bandpass filter and an LNA in each module, so you can just plug it in. Could you Peltier cool the LNAs? Decades ago, I bought a mini circuits LNA, and just for the heck of it, put it in the freezer to see if my refrigerator freezer to see if it changed the noise figure. I had a noise figure gain meter then, and it did. It mattered a lot. So I'm wondering, could we use Peltier junctions to cool the LNAs and get a lower system temperature? Could we connect multiple Kraken SDRs to fix my sparse array problem? 5 elements is a very sparse. We could share the clock. We could share the noise source. Probably be some irreversible changes to the boards, but I think it might be possible. Have internet access to the VSA, the very small array for SARA or the public. If it works, I could maybe store the data in a Snowflake public data marketplace share where you could just go get it from anywhere in the world. And also composite optical and radio images. I've been an amateur optical astronomer for most of my life. So thanks to you guys and for this opportunity to propose my idea. And I don't know, maybe it was Ted that is also optical. This was this last couple days, pouring 2 10-inch 1,000-pound piers for my observatory, for optical observatory. So that's it. I'd love to hear any constructive or destructive criticism, any criticism you have.
Dave, we're excited. This sounds great. Very few of us have talked about, have dreamed about actually imaging the radio sky. So that's exciting. As far as me being the optical, no, I'd go to Pablo. Pablo's even won awards these days for optical. So he's our master there. We're excited to see what you come up with. You have a bunch of work to do ahead of you. We're eager to see it happen. Well done.
Thanks.
Very good. Do we have Rich?
Yeah. Let's do it. We only got 7 more minutes, so anybody else have a presentation? If not, we'll just go through quick and just give a quick status, and we'll try to get through it the next 7 minutes. Jack Ansel.
I've got
2
some
things
quick
I'd like to
comments
show.
here.
Oh, I'm sorry. Nathan, go.
Yeah, so we were talking about the NOALEC LNAs, and I know that when I went to go look for a replacement, I couldn't find one either. So what I ended up doing was going with the GPIO Labs. It's also a filtered 1420 LNA SAW filter. Let me pull up. I've got some graphs to show that'll help. let's see here. I'm gonna go
Just
to
a few minutes. Show the picture, and then maybe put a link down.
Yeah. So I will. Well, yeah. So what you're seeing there is the new GPIO labs, the data off of it, and it is much more stable than what I've ever gotten out of the NOAALEC LNAs. It's also this is about 15, 16 days worth of data in here too, so it's been remarkably stable. There's no filtering whatsoever done on that. And another thing, we've been talking about temperatures. I've been going the opposite direction, and instead of trying to cool it down to something kind of like absolute zero, I've been trying to get that out of the way. I've been trying to get, that's not right. How do I get this thing to go away? I've been working on temperature stability. And so I actually have an experiment going on right now where I have temperature probes buried in the ground down to like 600 millimeters, so a little bit less than a meter. And so far I'm getting about 0.7 degrees Celsius difference between lowest and greatest, and that's over about 2 months. So I'll be putting some electronics in the ground and doing some drift scans to see how everything drifts during the day. But to be looking forward to that, because I think that's a lot cheaper and easier and more redundant solution than trying to use something like Peltier coolers or something like that.
All right, thank you. And realize it is temperature stability. So putting a heater and a Peltier that you can precisely control the temperature with a heat and a cold source is more important than having very cold. Because we don't have to worry about gain. We got a lot of gain for these antennas. The question is, can you keep that thing at the same temperature throughout all your observations? And so you need a hot and a cold for control functions. So, and you can even have it, warm as long as you can maintain it at the same warmth. Okay, Jack Ansel, you got anything?
Just briefly, I was reading in the latest journal about Edward Moll's work at the H167 alpha line, which really struck me. As an astrophotographer, I'm used to electron transitions like the Balmer transitions at much, n levels of 3 to 2, 4 to 2. 167 sort of blew my mind. So I was doing some research and I found a paper on Wolfgang's site about radio recombination lines. And one of the footnotes referenced a book called Radio Recombination Lines, which I bought. I got this for $11 on eBay. And I just say, if you're interested in this, it's an excellent book. There's one chapter, chapter 2, has got a lot of heavy math. Some of it's over my head. But in general, if this is something of interest, I'd say get the book. It's quite worthwhile. And that's all I have to say.
All right, thank you. And we're going to extend on a little longer just to get through everybody first. Tom, our illustrious SARA treasurer.
Yes, good afternoon. I really have nothing to add to the group, but Rich, I really need to talk to you. Give me a phone call when you can, anytime tonight, up to about 11 o'clock my time.
Okay. All right, I'll do it after we get through this. All right, Paul.
Hello. Yeah, so I'm working on a few projects, including a 12 gigahertz 1 meter dish, but nothing to report yet today, just listening in. So I'll turn it back to you.
Okay, thanks. Andre Powell.
I've now unmuted my. Okay. No, I've nothing further. It's been absolutely fantastic to you all. It's been wonderful to learn new stuff and the fact that there's someone actually doing the same kind of something that I'm doing. So brilliant. Thank you. I shall drop in next time. Thank you so much.
Okay. Dennis Hufnagel. Can't hear you. Hi, Dennis. Can't hear you.
Okay. How's about that?
Oh, got it now.
Okay. Anyway, thank you very much, Rich. This has been a great session. A lot of new stuff. I don't have anything to add. I do have some questions sometime about using a satellite dish and modifying it with a little antenna stub in the horn. I think I can do that. Anyway, I'll let you go. Thank you.
Okay. Thank you. Nathan.
Already gone.
Okay, we get Jameson Adcock.
Hey, nothing to report. Just I've been buried for the past several months, but just really appreciated and enjoyed the presentations today. So the only thing I guess I do have to report is I have been back in touch with the folks down at the Smithsonian, and we're going to try again. I think the best way to help them troubleshoot their system is to take my antenna and laptop down. That's very portable, and I know it works well. And just see what the source of noise is that they've been suffering from, because they just can't get their scope in the box to work without, just it's flooded with noise. So I don't know. I guess we'll find out, and I'll have something more to report next time.
All right. Well, let us know if they need help. You need more help.
Yep, will do.
Let's see. Did we get Dave already?
Yes.
And okay, Bruce. I got to.
Sam, yeah, I'm coming in here. Okay. We were talking about signal generators, and there's times you want to get an extremely weak signal, and shielding the generators will run you nuts. And I have a actually pretty simple solution for that. I don't know if it can be seen on here. I've got a piece of aluminum pipe, maybe 30 centimeter long, 30 millimeter diameter, and I've got a crystal oscillator mounted to a plastic ruler with a battery to power it and a switch and a plastic ruler. So this thing can be slid to the exact center of that pipe, and you've got essentially a waveguide beyond cutoff. So it's about 1 dB per millimeter loss through that in most frequencies. So you get a crystal oscillator with a harmonic that falls on the frequency you're interested in, and you can get an infinitely weak signal for all practical purposes, well below anything you can detect. And that's been a problem with any signal generator around. There's always leakage out the power cord, the dial, everything else seen on all the surplus generators. This is the only thing I've come up with that allows you to have a signal that goes all the way to zero signal strength. And sometimes that's handy. So it's something that's pretty cheap to throw together, or, $1 or $2 for a crystal oscillator from like DigiKey or Mauser, and mount it on a plastic stick with a battery and a regulator and a switch, and slide it on down the pipe. The other end of the pipe just has a little probe antenna on it. It works great for getting the infinitely weak signal. Not any good for a strong signal, but for very weak, it's pretty effective.
Great, thanks. All right, Bruce Rout, I think you're the last one. All right, maybe not.
Okay, I did have another comment there. At the beginning of last month, I was over in Germany visiting family over there. Just got back not too long ago, so I'm still a little jet lagged. But anyway, I did manage to get by Wolfgang's facility there and took a lot of photos. So when I get around to it, I'm going to take the group of photos and throw a few comments on them and send that off to go in the journal, if that's okay.
Excellent. That'd be great. All right. I think that's it. Anybody else? And by the way, everybody that's done this stuff, think of putting this stuff in the journal. Send it to me by the 12th of next month, and we'll get it in the journal. Okay. That's it for today officially. I'm going to turn the recording off, and I'm going to keep it running. We'll have an after sessions, call it after sessions party. Ted usually runs that because everyone talks about their ezRA stuff. So I'm going to turn off the recording, and thank you very much, everybody. This was an excellent session, and sorry for the running it quick at the end, but I think we got everybody in. All right, thank you.
Brilliant.
Thank you.
Thank you all.
Thanks.